So, hello everybody and welcome in our new classroom, first floor, Fischer-Richman Street 114. As you can see, today's title is Combinatorics. You have the date, and again I forgot to check which class is it, how many classes we have had so far. So, for the next couple of weeks we are going to talk about combinatorics. And I listed for you the 3 subtypes of problems concerning arrangement and picking of a certain number of objects. So the first one is permutations, where order matters, so you have to order a certain number of elements. N is a natural number. The second types are going to be variations that will come a bit later. Also, the order matters here, but in this case you have 2 numbers given, k and n. So let's say 3 out of n equals 5 elements. You have to pick them and then order them. So that's again going to be ordering. And the last one, combinations, that's a different matter because there order doesn't matter. So you basically just have to choose or pick k elements out of a given number of n elements. Typical example is a lottery where you have 90 numbers and you have to pick 5 and the order doesn't matter at the end. Okay, so let's see the first topic for us, permutations. In the Edivu video, he was talking about 10 different cubes. Since that's a lot to list here, I decided to choose instead 6 as a starting number to illustrate combinations and permutations within it. So let's say we have 6 balls of different colors, red, blue, green, white, yellow, and pink. And the question is, the very starting question, how many ways can you arrange these 6 balls if the order is important? This is usually how we indicate the slots where we have to put the chosen objects. So the first one, in the first place, you can choose any of the 6 colors. So you have 6 ways to choose that. In the second one, you choose from any of the remaining 5, then from any of the remaining 4, and so on. And obviously, in the last place, you have the remaining 1 ball to put in. Now, as Edivu also put great emphasis on the question of what operation you put between these numbers, and you have to multiply these numbers. And since in my experience it is not always clear why, and later when we have examples where you have to use subcases and addition also comes into the picture, therefore I would like to illustrate with a fewer number of cases with the branching tree illustration why this is multiplication and not addition. If for some of you this is obvious, I'm sorry for taking your time. Let me just clear the board and choose just 4 colors. Well, actually first only 3 colors, and see how you can represent the choices with a branching tree. Well, cleaning this board is not the easiest activity, but it will do. Okay, so let's see the example. Let's say we have the 3 basic colors, blue, green, and red, and you have to arrange them in a certain order. So in the first slot, you can take any of the 3. Then comes the second slot, and obviously if you choose blue, then you have 2 choices afterwards. You choose either green or red. Similarly, here you can choose blue or red, and here you can choose blue or green. So now notice that you had 3 possibilities here, and here out of the 3, 2 branches start. That's why you are going to have 3 times 2, multiplication. And in the third slot, you have no choices. In each case, you have to put in the particular color that you haven't used so far. So that gives you the final result. 3 times 2 times 1 is 6. And we have a notation for this. Namely, we say that it is 3 factorial. 3 factorial means multiply the numbers starting from 3 going down up to 1. Okay, it's pretty evident here why you needed to use multiplication. I'm going to add one more color and do that. It's still a manageable number of possibilities. And afterwards, you can imagine how it works for bigger numbers. So let's say we have a fourth ball white. Okay, then in the first layer, I had 4 possibilities to choose into the first slot when I ordered the balls. In the second slot, I can put any of the 3 colors I haven't used. So that's going to be, in this case, green, red, white. Here, red, blue, white. I hope I will have enough space. Here, blue, green, white. And the last one, blue, green, red. Okay, so again, it's nicely seen that these 4, each of them, branch into 3 branches. So the possibilities already count to 4 times 3 when you filled up the second slot when ordering the 4 balls. Now comes the third slot. Here you can choose any of the 2 remaining colors. So this is going to be red or white. Here you have white or green, green or red. Oops, not enough space. Okay, white, blue, red, white, red, blue. Things are getting a bit crumbed here. White, green, blue, white, blue, green, red, green, red, blue, and finally blue and green. Okay, you get the point. Every part, again, parts into 2. So that means that your possibilities got doubled. 4 times 3 times 2. And I'm not going to draw all the remaining branches, but you get the idea that here you have only one remaining possibility in each case, because every branch you travel down represents one possible ordering of these 4 balls: blue, green, red, and then here you have to pick white, here you have to pick the red, here you have to pick the green, and so on and so forth. So your final result is going to be, again, 4 factorial, which is 24. If it's not an extremely huge number, then please don't forget to calculate your final result at the end. Okay, so far so good. The second complication comes when some of your objects are identical. That's when we talk about permutation with repetition. Repetition meaning that you have some repeating objects or numbers, depending what you have to order, in your set of elements. In case of Eddie Wu, he had 10 cubes, and when he introduced repetition, he picked 4 identical whites first, and then 3 identical brown ones. Okay, so let's deal again with small numbers, and let's say that I have 2 red balls. Now, if you have 2 red balls, then in order to prove how you have to calculate this, let's suppose at the beginning that the 2 reds are distinguished. Let's say the second red has a sub-index red 2, like representing that ball is a bit bigger, or it's dirtier, or whatever. Now, this leads us back to the previous case where we had 4 different objects, with the only difference that every time you have a V here, now you have to have a red 2 obviously, since I just changed that into this bowl. This will take a lot of time for me to change, and I shouldn't use my fingers, but never mind. So these are all red now. And my point is that, of course, if I distinguish between these reds, then I am going to have again 24 possibilities. Now, I hope I have no W left. Okay, but now let's see. For example, in this case, blue, green, red 1, red 2. And in this case, blue, green, red 2, red 1, so this second ordering. The difference between the two is just the index. So the moment I delete the distinction, these two orderings become identical. And it's going to be always true for every pairing. So if I choose one where I had, for example, green, red 1, red 2, white, then I should also find a pair for this one where the only difference is going to be the order relative to these two reds. That's going to be this one. Green, red, red 2, and then, oh, I don't have white, sorry. It's blue. And blue here. So this one, again, these two will end up identical once I forget about my distinction between the two reds. So the moment I have two identical reds, the original 24 possibilities seem to halve. Again, one more when they are not next to each other. Let's say this one, red, 2, green, red, and then blue. This is one ordering of the 4 elements. And then I will find another one which starts red, green, red 2, and then blue. And again, these two only differ in the relative order of these two reds, so they become identical the moment I forget about this index. So the conclusion is that if you have two elements, then this 4 identical, then this 4 factorial has to be divided by the number of which they can be ordered relative to each other, in this particular case 2. Now I will write 2 factorial in here instead of 2, which is the same because we know that 2 factorial is actually 2. Because in general, when you have a different number, then you need factorial there. So what do I mean? If you have 3 identical reds, then you have 5 objects to order. The possible order of 5 different objects is 5 factorial. But the moment you order these 5 objects, you will have always orderings in which these 3 are ordered relative to each other differently, but they are not distinguishable. So you have to divide this number by the number of possible orderings among 3 elements, which is 3 factorial. So let's calculate this. One way to calculate is to calculate both numbers and then divide, and that's 20. Or a quicker way, if you think about this, that this is a multiplication and this is also multiplication, then you can simplify, and again you end up with 20. Okay, I will stop this video now.